classes is that we start with a really rigorous workload and maintain that throughout the semester rather than like ramping up to a ton of stuff at the very end. So the workload that you've gotten used to is what it's going to continue to be the rest of the semester. So, if that helps. You're doing great so far. Any questions about class science material, about lab?
Since we are off next week, will there still be an aide in the lab Monday and Wednesday?
Up to you. Who would actually go to those open lab sessions if we ran them over the week or off? Monday? Yeah. Should we just say Monday? Does that work for everybody? Okay, and then she can, because I'm fine, and I'm sure Christina's fine to come, but I don't want her to show up and nobody be there. So let's say she'll come in Monday and not Wednesday.
And we can still go to that Tuesday one as well?
Yep. Right. All the origins, all the insertions, all the actions, but they can just be that bony projection, not the superior portion of the trochanter.
So you don't have to know.
Just the trochanter is fine.
Anterior, lateral.
Right. Right. So I'd like to know all of them, but it can be just that specific bony projection. And if it's by the ligament to that bony projection, just the bony projection.
Oh, so you don't have to know the
So is that like the gapway, tubercle, the gapway?
Well, so the tubercle is the projection off of that bone, so still the
Gapway.
Yeah.
There's like a lot of them that
I mean, it's never going to hurt you, but what I'm looking for is the bone. But no. Alright, other questions? Like somewhere Yep, sorry for the delay in the worksheet. I managed to get your test graded fast, even though I told you I wasn't going to, but that was the repercussions of the terrible advising week, was the slow posting of the worksheet. But it will be done this afternoon. Other questions? Alright, so we're going to get into the heart. So this is more lab type information, but I wanted to put this picture up just because it's counterintuitive. So the apex of the heart is actually the bottom of the heart. It is where it kind of comes to this shallow point. And then the base is actually the top of the heart. And when we get to systems and lab, that will be something that you need to know. And I just wanted to draw it to your attention so you don't get confused. And then we refer to the borders of the heart, right? Left inferior and then superior. It's here where the heart is, not where the great vessels are going. And then this is the typical view that you'll see of the heart. We'll look at a few others, but this is kind of how it sits within the thoracic cavity, so that's normally how it's oriented. All right, so walls of heart. We already saw in lab the pericardial sac. We saw it not in the cadaver though. This is what it would look like if you freshly dissected a cadaver and hadn't removed any of the layers. So this is the pericardial sac. Dissected, laid out like that. And then the heart is going to be surrounded by a layer of fat. And that's for everybody, that's not just for fat people. So everybody has a layer of fat surrounding their heart. Some people have more, and sometimes that's an issue, but everybody has something about it. So you have that pericardial sac, and that's a serous membrane. So that serous membrane makes what? Serous fluid, and what's the function of that? Prevents friction. So that heart is going to be beating, and you don't want it rubbing against the pericardium because that'll cause friction and tissue damage, and it's very painful, and we'll talk about when that happens and how that happens. But that pericardium has two layers, and they're going to be a dense fibrous layer that's for kind of structure and protection, full of areolar tissue, and then the mesothelium is the actual serous membrane that makes that pericardial, forms the pericardial cavity, making the serous fluid. All right, so remember, muscle is a connective tissue, so all this is connective tissue. Well, muscle is not a connective tissue. There's connective tissue between the muscle and you. So then the myocardium is where the blood vessels and nerves are going to be found, plus that cardiac muscle tissue surrounded by connective tissues. And then we have the endocardium, which is an endothelial layer, and they're surrounded by areolar tissue. So you can see that most of the structure of the heart is going to be muscle. It makes sense because its main job is to contract. So think about skeletal muscle and how when you look at those fibers, you can kind of tell what direction it's going to contract in. So the myocardium, the skeletal or the heart muscle fibers are going to form kind of these circular structures. So why are the fibers arranged like this? Yeah, go in different directions and squeeze. All of those are good answers. So really what needs to happen is it needs to be squeezed out of there, it needs to be squeezed out of here, and then squeezed up into the vessels. So rather than being parallel muscle fibers that can just get shorter, instead they're forming these circles so it can squeeze. So cardiac muscle tissue is close to skeletal muscle tissue. It has some differences. It's got myofibrils that are arranged into sarcomeres. It has a striated appearance, just like skeletal muscles. It's got a very red color, rich in capillaries, because it's got a high oxygen demand. And then it has this extra structure of intercalated discs. So if we zoom in even further, here's the cardiac muscle cell and the intercalated discs running between. And it's full of mitochondria because it's got high energy demands. Bundles of myofibrils, actin and myosin. And then these cells are very small, 10 to 20 microns. And rather than being very, very long cells like the skeletal muscle cells are, instead they're pretty short and fat cells. So we've referred to these intercalated discs a lot, and we haven't really talked about what they are. So intercalated discs are going to be made up of the Z lines of the muscle cells anchored into each other with desmosomes. And remember, those are protein structures that anchor cells in. And then there's also going to be gap junctions that connect these cardiac muscle cells. So then these structures, the desmosomes anchored into the Z lines with the gap junctions, allow the plasma membranes to be intertwined. So what function do those intercalated discs perform?
They allow the cardiac muscle cells to contract in a wave-like pattern.
Yep, so rather than needing to innervate each cardiac muscle cell, one can signal the next, can signal the next, can signal the next, and they can all contract together and form a similar function.
So do they work as a pump, basically?
So When they contract due to the structure of the heart, you get that pumping. So then these intercalated discs are unique to the cardiac muscle cells. These aren't found in skeletal muscle or in smooth muscle. So this is one of the main hallmarks of cardiac muscle cells. So then this is a way that you can kind of imagine what the pericardium looks like. So remember, it's a double layer. So there's the parietal pericardial layer, which is on the outside, and then the visceral pericardial layer on the inside. And then those are contained, within those are serous fluid, that's the pericardial cavity. And then there's serous fluid around the heart, which is represented by this here. Alright, so here's those layers again. Now we've got the full structure of the heart to help us visualize it. So we've got the parietal pericardium, we've got areolar tissue, the mesothelial layer, which is going to make the serous fluid. And then that pericardium is going to be anchored in to the central tendon of the diaphragm to help stabilize the heart and keep it from moving around within the thoracic cavity. All right, so pericarditis is an issue that can happen with the pericardium. And it feels like you're having a heart attack. So there's a pain in your chest. And it usually is associated with a fever and coughing. And then it can be relatively easily diagnosed because when you listen with a stethoscope, you can actually hear a rustling or a rubbing of the heart every time it beats against that pericardial sac. So this is very painful, and there's no stopping the heart from beating and rubbing on it. So depending on what causes it, whether it's an infection or some issues with smoking or something like that, the treatment for it is different. Here are chambers of the heart. And because we haven't gotten to this in lab yet, I wanted to go through this a little bit, even though it's more anatomy type information that we usually keep to lab. I want to be able to say the structures and you know what they are as we go on with this lecture. Okay. So we start where the deoxygenated blood is coming in through the superior and inferior vena cava. Please go into the right atrium. This is the fossa ovalis, and it's a closed hole, usually. We'll talk about when it's not in a minute. And then that right atrium is surrounded by these pectinate muscles. Those are cardiac muscle cells that can contract and help push the blood out of the right atrium. What keeps the blood in the right atrium is the right AV valve or the tricuspid valve. I'm fine with either of those terms. I kind of like right AV valve better because it's real easy to remember where it is between the atrium and ventricle on the right. But either is fine because tricuspid is more commonly used. Okay, so right AV valve is what keeps it in the right atrium. When it contracts, when the right atrium contracts, these papillary muscles are going to be what's in charge of controlling that valve opening and closing. Those are found in the right ventricle. Blood then moves down into the right ventricle. The right ventricle contracts. The right ventricle is the weaker of the two ventricles because where's the blood going from the right ventricle? To the lungs, so pretty short distance. So that blood is still deoxygenated. It comes out through that pulmonary trunk to the pulmonary arteries. Those branch out into teeny tiny capillaries that run next to the alveoli, drops off CO2, picks up oxygen, and now we're going to come back in through the pulmonary veins to the left ventricle, left atrium, thank you, down to the left ventricle. And what's controlling that is the left AV valve, or bicuspid valve, or a third name for it is mitral valve. But I feel like that's the really old name that you don't hear as much anymore. Alright, so then the left ventricle is the strong ventricle. It contracts, pushes the oxygenated blood out through the aortic arch. Then it branches off to the head, branches off to the body, goes to everywhere, all through the systemic circuit to drop off that oxygen and pick up CO2. Alright, so that foramen ovalis here, or fossa ovalis, can sometimes be open. So normally, when you take your first breath after you're born, that foramen ovale closes and forms the fossa ovalis. It's just a little divot in the right atrium. But about 25% of people, it doesn't close within the first 3 months. And this is usually not a big deal. You get a little bit of backflow of oxygenated and deoxygenated blood, but your heart just compensates for it. The issue is that about 40% of stroke sufferers have a patent foramen ovale, meaning it's still open, especially those people who have a stroke younger than 55. So my brother had a stroke when he was, I think, 21, maybe 20. He's very healthy, didn't have high cholesterol or anything like that. He just all of a sudden was working in his engineering lab and just kind of passed out. And they didn't even suspect a stroke because he was so young and healthy. And then sent him home and then brought him back and found that he had suffered a stroke. They think he was just weightlifting and got a small clot. And normally that clot would have ended up in his lungs. So it would have gone through, ended up in the small vessels of the lungs. But instead, it bypassed that pulmonary circuit, went back into the systemic circuit, ended up in his brain. He's fine now. He lost some function in one of his hands and eventually got it back. But they found that he had that patent foramen ovale. Alright, so like I said, the right ventricle is the weak ventricle, and that's fine because it doesn't need to push blood very far. And the left ventricle is the strong ventricle. It's got a thicker myocardial layer.
So for that path, the hole, can they like fix it anyway, or do you just have to be like aware of it?
Yeah, you can fix it, and they gave him the option to fix it, but it is open heart surgery that you need to do. So they gave him the option to have it fixed, but the risks with our open heart surgery are pretty high. So he decided just to take baby aspirin forever. So if we look at dilated, relaxed versus contracted, you can see that the size of these ventricles change quite a bit. And just like our skeletal muscle, our cardiac muscle, when it contracts, the cross bridges form, actin and myosin overlap, and the muscle fibers get shorter. So because of the way they're arranged, though, these constrict as a circle and make the chamber much smaller. That's what pushes the blood out. Now our heart's on 100% efficient. You always end up leaving some blood in there. And some people's hearts are more or less efficient than others. So you never completely close off these ventricles. There's always some blood left behind, and we'll talk about how that affects your cardiac output. Questions so far? Watch a short video that just shows the path of blood and how the valves are involved in it.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
The human heart has 4 chambers. The 2 upper chambers are the atria, and the 2 lower chambers are the ventricles. The interatrial septum separates the 2 atria, and the interventricular septum is the partition between the 2 ventricles. The right atrium and right ventricle are connected through a tricuspid valve. As the name suggests, it has 3 leaflets or cusps. On the other side, the left atrium and ventricle are connected through a bicuspid valve. The bicuspid valve is also called the mitral valve because of its resemblance to a bishop's 2-sided mitre or hat. The leaflets of these atrioventricular valves are connected to fibrous tissue called the chordae tendineae, which in turn are attached to papillary muscles. Contraction and relaxation of these muscles make the valves open and close. There are also valves at the opening of the pulmonary trunk and the aorta. These are called the pulmonary valve and the aortic valve, respectively. Because of their crescent moon shape, these 2 valves are also called semilunar valves. The characteristic double-up sound of the heartbeat is produced during the closing of the heart valves. The thickness of the walls of the 4 heart chambers varies with their functions. The walls of the atria are thinner than those of the ventricles, as the blood needs to be pumped into adjacent ventricles only. The left ventricle pumps blood a greater distance at higher pressure. Therefore, the wall of the left ventricle is thicker than that of the right ventricle. The sinoatrial node, atrioventricular node, bundle of HIS and Purkinje fibers represent the specialized cardiac tissue. These fibers are autoexcitable as they have the potential to generate electrical activity without any external stimuli. This makes the heart beat continuously.
So one thing I like about that video is that it shows you how you've got oxygenated and deoxygenated blood in the heart at the same time. So whenever we talk about it, we kind of follow the path of just one piece of blood through the heart, but while you're pumping deoxygenated in, you're also pumping oxygenated out. Okay, so then when the heart beats, the AV valves are going to close, then the semilunar valves open, then the semilunar valves close, and then the AV valves open. So the AV valves are going to open at the same time, the semilunar valves are going to open at the same time, and that's why you hear lub-dub and not 4 separate sounds. So the valves are actually pretty delicate structures, and they're a place where you can have congenital malformations or buildup of plaque or some damage. And if they don't close all the way, you can get backflow of blood. Your heart starts to be less efficient. With every beat, you get less oxygen to the tissues, so then the heart beats harder. And that's when you start to worry about having a heart attack. If your heart is straining just in normal life, it can start to fatigue and wear out. But we have really good replacement valves. So oftentimes these are bioprosthetic. So they're a combination of biologicals and prosthetics. So oftentimes they'll have a kind of synthetic casing and then a biological valve from a cow or a pig. So because they're biological and they're not your own tissues, they can wear out. So they can last about 10 years. So within the heart, there's this cardiac skeleton, and it's not a skeleton of bone, it's a skeleton of dense connective tissue. Gives the heart structure, stabilizing the valves and the muscle, and more importantly, it electrically isolates the ventricle myocardium from the atriomyocardium. Why is that important?
Prevent premature relaxation, so it has time to depolarize and contract.
Yeah, so you don't want your atrium and ventricles contracting at the same time, right? Because then all the blood would just squirt out of the heart in every single direction. So you want it to have a sequential contraction. You want the atrium to contract and relax, the ventricles to contract and relax. We don't want everything to contract at once. So this keeps those cells from signaling the other cells to contract, which they can do because of those intercalated discs, right? All right, so systole is going to be our contraction and diastole is going to be the relaxation. So in systole, the blood moves from the adjacent into an adjacent chamber or into a trunk like the atria or the aorta or the pulmonary trunk. In diastole, the chamber fills with blood and prepares for the next contraction. So this is what it looks like, relaxation. Blood passively fills into the atria. Atria contract, the AV valves open, blood moves into the ventricles contract, blood moves into the pulmonary trunk and the aorta, and then we go back to relaxation. We call that the cardiac cycle. So it's more appropriate to visualize it like this because it's not like it goes from start to end and then it's done. It's constantly cycling in and out of systole and diastole. So we start kind of arbitrarily when that deoxygenated blood comes in. It's not like that's the very first thing your heart does. It just, that's where we tend to start the cardiac cycle. So then we start with atrial systole, and the atrium relax, then the ventricles contract, then the ventricles. So we look at what's happening in the actual heart during each of these steps. Blood is moving into the atrium, then they contract, those AV valves open, then the ventricles are filled with blood, and then there's a short stage called isovolumetric contraction, where the ventricles are contracting, but there's not yet enough pressure to open the semilunar valves. So they're pushing, but all 4 valves are closed, AV and semilunar valves. So the AV valves are going to be controlled by muscles. The semilunar valves are just like barn doors. It's pressure that opens them. So the ventricles contract, they're pushing, but the ventricles don't have enough pressure to open those semilunar valves yet. When they finally have enough pressure, those barn door semilunar valves flap open. Deoxygenated blood goes to the pulmonary circuit. Oxygenated blood goes to the systemic circuit. Now we have isovolumetric relaxation. So what does iso mean? The same volume, same amount. So the volume in any given chamber isn't changing. And the reason for that is all 4 valves are closed. So all 4 valves are closed in isovolumetric relaxation as well as in isovolumetric contraction.
Would you like us to note what's happening at each step?
Yes. So now we're in ventricular diastole. The atria are passively filling with blood, and then the atria will contract again, and we're back into the beginning. So remember, on the right atrium, we've got the deoxygenated blood. On the left atrium, we've got the oxygenated blood, and this process is happening at both sides at the same time. So then, when we're listening to heart sound, we're listening to the valves flapping closed. So what if you hear lub dub dub? So what is that called? Heart murmur. Yep. And sometimes sometimes heart murmurs are just fine. Lots of people have them when they're born and they just have them their whole life, and your heart just compensates. And if those valves aren't fully in sync, it's not a huge deal. But if you start to get a heart murmur later in life, then you start to worry that there's damage to one of those valves.
So the lub would be like the AV valve.
This figure overlays both of those things. So here's the lub, AV valves, the semilunar valves. Alright, so this figure is showing the pressure changes in those different chambers. So this is a really good way to test your understanding. So this only shows the left ventricle and the left atrium, but a similar thing would be going on in the right at the same time. Alright, so take a minute and see if you can explain this figure to the person next to you. So see you have pressure changes, left atrium, left ventricle, and the aorta. Try and follow the path of blood and note where the valves are changing. Okay.
It's red.
The ventricle?
Left ventricle gets like a lot of pressure.
You need to be able to identify yeah, we'll need to be able to talk about it.
So when the blood's coming out of the left atrium, I think that's where it's going down a little bit. And then pressuring the ventricle increasing. It's going out of the atrium.
Maybe that's light, that's coming right, yeah.
And then at 5 it ejects. And so that's why. I don't know, I feel like I wouldn't be guessing that way higher.
Yeah, and then it like spikes. Oh, I guess that's what I'm talking about. The volume in the ventricle. That makes sense.
Oh.
Because that's gonna cause it to move. Systole when it's contracted, right?
And then ventricle. Isometric fixation is when it'll start. Passive ventricle.
I think that's like where you start getting.
Yeah, the ventricles are on the bottom, so that's what they had to go to the atrium.
It goes to the. But I think it means like there's gonna have be some in there, like it's never gonna be complete, you know. Like I think the atrium has to push blood into the ventricle to start
questions?
The actual.
Surely at least one question. Yeah.
The aortic valve versus the semilunar valves are those.
So the aortic is a semi.
Okay, that's what I thought.
Yep.
Okay. What's the diaphragm?
Yep, I was hoping that somebody would notice that and ask about it, that's why I said there's gotta be some question. Alright, so the diaphragmatic notch, when the heart, or when the ventricles left ventricle pushes blood into the aorta is so elastic that it is low pressure for a second because it stretches out and then it recoils back. So that's what this notch is. It goes wow, and then makes a blip because the left ventricle is so strong and the aorta is so elastic. Other questions?
This is only for the left side,
Yep, the same thing is going to be going on in the right side. Yep,
but it's just not gonna be as much of a pressure.
the pressure would be different due to the strength of the right.
So for the last step on 8, when it says passive ventricle filling occurs, so is that like always happening, but then the atrium have to contract to like push it through?
Right. Yeah, so blood is going to be coming in through the vena cava or from those pulmonary veins, and then it just kind of falls down to the ventricles, and then the atria contract to push the remaining blood out.
What are those small third and fourth heart sounds?
So these are going to be the opening of the valves make a little
Makes sense.
noise, but the closing of the valves makes bigger.
What was that thing one more time you said about aortic and semilunar valves? You said they were the same?
Yep, so the semilunar valves are the pulmonary valve and the aortic valve. And then the AV valves are the bicuspid and tricuspid.
The aortic or the semilunar valves open.
Mhm.
So why is the pressure still increasing whenever it's opening?
Here?
Yeah.
So that's basically the pressure is increasing as the ventricle contracts. So it's getting higher and higher pressure, and the blood is leaving. So then it starts to drop once all the blood is gone, and the pressure is now moved to the aorta.
Okay, so the semilunar valves open, and at 5, that's when the actual contraction occurs.
It's through this whole time it's contracting. So through this whole systole phase. Yep.
So to get that last bit of blood out, it contracts harder.
Yep. So pressure builds and builds and builds. Yep. And then it seems like a long time for a contraction to happen, but remember we're just in milliseconds. Alright. So then to test your understanding, what does isovolumetric mean? Same volume. And what are the valves doing during isovolumetric? All 4 valves are closed. And then there's 2 stages. One, the ventricles are contracting, so that's isovolumetric contraction. And the other is isovolumetric relaxation when the ventricles are relaxed. So that's going on at 4 here and at 7. So you just did this, describe the route the blood takes. So how does the heart coordinate these specific contractions? Yep, intercalated discs are going to be how the cells communicate with each other. Yep, the nodes. So you have nodes of neural tissue that are going to control whether the atria and the ventricles are contracting. And then the heart is electrically isolated because of the cardiac skeleton. So intercalated discs, neural tissue, which we'll talk about all the different nodes, and the cardiac skeleton. All right, you guys can take a quick 5-minute break. Be back here at 46.